this on? Hello? Yeah. Okay. Time to get started on our second to last day, and it's a morning of finales. I think this is the last in Professor Macintyre's series about history of interactions of logic and number theory.
Thank you. Is this audible? Okay, thank you. Well, I imagine I'll finish these lectures at very high speed, possibly writing with both hands or something. So at the beginning, I'd just like to repeat my gratitude for the chance to come here and to meet so many interesting people. The publicity for the meeting beforehand didn't really make it clear that the local community consisted of such lively, interesting, charming people, and I'm very glad to have met them, and I look forward to seeing them again. And I think many people in this audience owe a great deal to the United States in terms of our education. I feel that I certainly would not have been what I have been if it had not been for the generosity of the United States in educating me and supporting my students over many years. And I think probably most people feel this. This room is full of people from numerous countries who have been totally happy doing communal activity over the last few days, and it's just extremely regrettable that we have to wake up this morning to what is now facing the people of Iraq. Okay. All right, so I want just to say a couple of things about, to finish on this characteristic P stuff. I feel that the last lectures of Francois were so comprehensive and so suggestive that I have very little to add to it. I mean, the theory that he and Denef put together, this motivic, the theory via the motivic integration, gives the kind of uniformity that one might hardly have dreamed of for the uniformity in P. I want just to mention a couple of other things a couple of other uniformities in P that are known, have been done. They're somewhat connected with what Francois said, but not completely. And so I will simply mention them for the record. One is the following. I will use the formalism I used yesterday for the ultra products. I mentioned at the end yesterday the idea of considering uniformities about Frobenius as P goes to infinity. I won't say much more about that, but thinking about that over a number of years led not only to the discovery of ACFA, which is certainly proven to be important, but it also led to maybe slightly stranger considerations. Over time, the study of pseudo-finite fields has gone from considering sort of qualitative consequences of Weis-Riemann hypothesis, so that these are really the axioms for pseudo-finite fields, to deeper things. One wanted to bring in the action of Frobenius in some way or another. The pseudo-finite fields are there only really because they are the fixed fields of some generalized Frobenius. And that in turn will lead one to consider the various cohomology theories, L-adic cohomology theories, which are associated with a deeper understanding of the geometry of finite fields. So in the course of thinking about Frobenius and its uniformities, I was led to think about uniformities in these cohomology theories. I won't go into it very much, but the following picture exists and is now being studied, and it has some loose connections with issues around Grothendieck standard conjectures. So as usual, we have this space consisting of the prime. The index set consists of the primes. Now, the ultra-product construction is so fantastically functorial that it even allows one to make sense of the following thing. You basically put over P, let us say, p-adic étale cohomology. And then create over a more general D another cohomology theory. So you'll get sort of d-adic Now, it's not clear that this has any meaning, and it requires a lot of painstaking work to give it a meaning, but nevertheless, there is such a picture. And there are the issues of uniformities in these results is somehow linked to the Grothendieck standard conjectures. There's a reference in the notes to that. And one hopes to continue with this. Ivan Tomasic has done significant variants on this. And I imagine there's a great deal to be done on this. The logicians till now, of course, have relatively, I certainly have relatively shallow knowledge of these matters, but certain formal aspects of them allow you to do something. Okay. Another thing concerned with the characteristic P or p-adic situations where you can go further, you can study, you can analyze in the spirit of these lectures, in the spirit of the logical tradition, that's to say logical analysis of definitions, one can analyze the maximal unramified extension of QP, and even uniformly in P. So for an individual P, this was done by Simon Cochin in 1974, and well, various people have been involved in the uniformity aspect of it, again, Pass and I and Denef, Lazare, and others. In a similar spirit, one can consider the width vectors over the algebraic closure of QP, but equipped with the width Frobenius, the sort of the Frobenius that starts life on the residue field but then twists up. So this is a difference, well, it's a difference valuation ring, if you like, but you go to the quotient field, and Tom Scanlon and I and Luc Belair have succeeded in doing basically an X-quotient type analysis for this entity, and also proving an X-quotient theorem of the kind I mentioned yesterday, relating this to characteristic P variance. That is a paper which is still in the process of being refereed, but it's certainly available from Thomas's website at Berkeley. Sorry, FPL, sorry, thanks Bjorn, of course, yes, sorry. One could, well, yes, I mean, our methods are very, very general. As X-quotients were, we have, in order to study the basic sort of core things, it's rather natural to study all sorts of other artifacts that come up. And again, I would hope that this will be further studied. Now, I'm going to say something shortly, unfortunately not very much, about analytic aspects. Analytic situations over QP. So p-adic analytic functions, or certain p-adic analytic functions studied from the standpoint of model theory. There has been a great deal achieved in this. I'll say something about it. There's slightly more in the notes. Okay. Now, this is supposed to be a historical account. certainly to now has been largely biased in favor of the, let us say, the Robinson-X-Cochen school. Largely because in the early days of the subject, at least, it was that kind of model theory that led to the interactions and the applications. Now, I certainly cannot, with a good conscience, give these lectures without mentioning something else which happened. And it happened basically in the same time period as X-Cochen. It was, aside from X-Cochen, it was certainly the piece of work in logic that most affected me as a graduate student. This was the paper, well, was it 1965 or 1963? I can't remember, by Michael Morley. This basically created a new, well, gave a new dimension to pure model theory, and it was also extremely natural to use his methods in interaction with algebra. Morley was recently rewarded by the AMS for this seminal paper. He shared the Cole Prize, I think, the Steele Prize with Ronald Jensen. And I think if it came to a vote in the model theory community for perhaps the most beautiful paper of the last 50 years, this paper of Morley's would be it. And let me just say very briefly what he did. It initiated essentially 40 years of very serious work. It led to the work of Schellach, the work of Hrushevsky, Zilber, Pillai, and many others. And this is the kind of work which has led to the sort of applications that Anand and Thomas have been talking about. But I cannot possibly do justice to this. I just want to make a picture which will slightly relate it to things we discussed yesterday, and then I will pass to discussion of analytic things. Morley set out to resolve a conjecture made by Wash, the same Wash whom I mentioned yesterday, Jerzy Wash. Among the structures I've been dealing with, the fields, the complexes, the p-adics, the reals, and so on, the complexes have a special nature. I've tended to stress the fact that topology is not definable. On the other hand, model theoretically, one of the most important, perhaps the most important thing after the basic definability about the complexes is that they are the unique algebraically closed field of characteristic 0 in power continuum. Any other one is non-canonically, of course, isomorphic to it. And this comes from the Steinitz theory of transcendent spaces, right? Now, of course, in the p-adics and the reals and so on, there is a certain, and in the fields equivalent to them, there is a theory of transcendent spaces, naturally enough. But transcendent spaces do not control the isomorphism type of the field. It is quite straightforward to construct models of power continuum elementarily equivalent to the p-adics, but not isomorphic to them. So the complex field, and more generally the algebraically closed fields, were the only visible fields that had this property. They had an isomorphism theorem. There was a unique model in each uncountable cardinality. And the reason is the Steinitz theory of transcendent spaces, a theory of dependence, etc. Okay? Now, Wash, model theorists were studying the class of so-called categorical theories, or kappa categorical theories. That is to say, theories which have a unique model in power kappa, up to isomorphism. And there are sporadic examples in nature, both for kappa equals Aleph 0 and for kappa uncountable. Wash had the wit to imagine that it might be the case that uncountable categoricity, or in categoricity in some uncountable power, was linked to something like a Steinitz theorem, abstractly. And therefore, if you had categoricity in one uncountable power, you would have it in all uncountable powers. That was basically the Wash conjecture, which Morley solved positively for countable languages. The conjecture itself is not necessarily so marvelous, but the methods Morley introduced are really marvelous. And I want to just give a very brief picture of it and recommend that you go then and read one of the many good books on the subject now, one of Anand's 2 books, or the beautiful book of Bruno Poisat, and so on. Okay, Morley set about trying to analyze notions of dependence, algebraicity, and so on inside general theories. Now, and it was really done in a sort of Tarskian perspective. So let me just rush through this. I just want to give a sort of geometric picture, just the very first idea. Suppose L is a language. Tarski, you have a thing called, now the Tarski space, say for L, this is the space of complete theories in L. It's the set of complete theories in the language L. In L, topologized like stone spaces. A basic open set is the collection of complete theories containing a given sentence. Basic opens determined by sentences. Now this idea is already very prominent in Tarski in the 1930s and the 1940s. This is a compact space, compact, totally disconnected space. That is really the compactness theorem of logic. So it's a space of exactly the same kind as I was playing around with yesterday, the Stonecek compactification. Now, it's more natural to, if you have a particular theory, perhaps incomplete in this language, S of t, S0 of t, this is a set of axioms in the language, not necessarily complete. This will be the subset of this, of theories containing t. It's actually a closed subset of this. Closed subset of spaces containing t.
So the open subsets are those that don't contain a given sentence?
Yeah, but basic opens are clopen because of logic has this negation. See, that's the point. Yeah. Now, Morley was trying to get at how you might have an isomorphism theorem, how it might be connected with notions of the notion of dependence being particularly simple. And what was it about algebraically closed fields that made its dependence relations particularly simple? Now, the picture is, we want to start looking, this is only telling you the sentence is true, the sentence is here. You want to think of being in a particular model and trying to track the behavior then of an element in that model, what formulas it might satisfy. And then to look at two elements and look at the formulas they may satisfy, or three elements and the formulas they may satisfy, or more generally, a set of elements and the formulas they may satisfy. So you go to S1 of t, this will be you extend the language, extend by, let's say by a constant, which I'll write as a variable, v. And now you look at extensions of t in that language. You say no more about v to begin with, but then you might complete. You would just say everything about v to complete. Okay, so S1 of t will be, it'll really be S0 of t in the new language. Okay, and there is a map, a natural map from S0 of t, from S1 of t to S0 of t, just a forgetful functor. Throw away all the sentences involving this constant. Okay. Now, how do you get a typical element in S1 if you're working with algebraically closed fields? You say what the algebraic properties of that thing are. You might say, for example, v squared equals 2. And that's basically all you can say about v in an algebraically closed field. Or you might say by an infinite set of sentences that V is transcendental. It doesn't satisfy any polynomial over Q. That would give another point here. In fact, really the only points, if this was algebraically closed fields of fixed characteristic, there would only be one point in this space. But in the next space, there would be infinitely many. There would be one for each irreducible polynomial, say over Q, and then one for the transcendental. Okay? And then you repeat this. You go to S2 of T. You look at two tuples, S3 of T, and you can deal with arbitrary tuples. And you have a huge amount of functoriality because of identification of variables, putting variables equal, and so on. There's a kind of some kind of huge covering apparatus of stone spaces here. But the one you get for algebraically closed fields has very special properties because the algebraic equations like V squared equals 2 and so on give you isolated points of this space. All you can say about a point V, you can say nothing more about a point V if you said it V squared equals 2. You're not able to say it's positive or negative square root of 2 in that language. And it turns out in the particular case of algebraically closed fields that the isolated points are dense. There's isolated points, then there's one limit point at the end. It's a bit like spec of Z. All right. Morley gave a categorical topological analysis of these things and introduced totally abstractly a notion of dimension for elements or tuples and so on in theories based on essentially a topological analysis of this situation. Now, by using the Cantor-Bendixson theorem from general topology, a non-trivial theorem, and by using techniques that preceded them involving Ramsey's theorem and so on, Morley was able to give a beautiful solution to the Wash conjecture using this kind of apparatus. Now, this created the notion of omega-stable theories, theories which have a decent dimension structure. Algebraically closed fields have them. None of the p-adics have them. The reals doesn't have it. In fact, none of the other structures we've been dealing with till now have it. After Morley, Schellach greatly generalized the notions of dependence and so on and changed this picture significantly. But everything he did could be said in terms of this picture. This led to the notion of stable theories. Much later, and also in passing, Schellach invented a notion of simple theory, which is not at all simple. And there were hardly any examples known until shortly after 1990, Hrushevsky realized, based on an analysis that Van der Vries and I and Chatsidakis had done of pseudo-finite fields, we were trying to count points in infinite pseudo-finite fields, and we did some refinements of the usual model theoretic analysis. Based on that, Hrushevsky realized that pseudo-finite fields, although not stable, are simple, and ACFA is simple. This allows you to bring to bear on these theories a huge and very sophisticated piece of mathematics. This whole development in model theory that started with Morley. Now, this is at the basis of the kind of work that Thomas is speaking about. I cannot do any more. It's a subject which attracted me enormously when I was starting. I knew Morley, and I loved his paper, and I tried to apply it to algebraic situations, but I have not been more than peripherally involved in the development of the pure theory. But the pure theory has vindicated itself, and I regret that I don't have the time to say more about it. Okay.
Can I ask one question about that arrow, which we get for Is it obvious that it takes complete theories to complete theories? When you forget all that?
Well, yes, there'll be many. Of course, a given complete theory here will come from many different ones up above. Yeah. Well, you see, complete just means that any sentence where its negation is in. If it's true here, it's certainly true here for the sentences in the restricted language. Yeah. Again, I want to say that if one has a certain aesthetic, you can really do most all of model theory inside this kind of picture with these functors of Morley. And Morley, from time to time, later in his career, did do things like this. This point of view also was very much in view in the work of Simon Cochin, who never worked in stability theory. But his idea was that the notions of model theory could all be seen in sort of abstract Boolean space terms.
One other question of
Mhm.
historical nature. Do you know who was the first person to consider this kind of space, this kind of topologies?
Well, I mean, Stone was operating in the 30s, and Tarski was operating in the 30s. I don't know the exact history. I guess Stone and Tarski must have known each other in the... I mean, Stone's duality... Well, Czech, I think, also presumably had some ideas on this. I don't know. But I tend to credit Stone with giving the full polished picture for the duality between Boolean algebras and compact totally disconnected spaces. Maybe one final remark here, and this is intended to be quite suggestive. I mean, Galois groups are profinite. They're Stone objects. The underlying spaces of absolute Galois groups are like this. Conjugacy classes in those groups are also like this, and so on. And in some cases, the spaces attached to, for example, the space S0 of the theory of pseudo-finite fields of characteristic 0 is homeomorphic canonically to the space of conjugacy classes of closed cyclic subgroups in the Galois group of Q. So in some cases, this abstract point of view connects very tightly with rather deep issues in number theory. All right, so I have maybe 35 minutes. I think I started a few minutes late. I want to give a very, very rapid discussion of analytic aspects, which constitutes a rather, a really very big success story. Is maybe not quite so closely connected with arithmetic, although I think it's certainly fair to say that, say, the p-adic exponential or the complex exponential are very closely connected with arithmetic. All right, so this leads us, we go back, right back to Tarski's work. So I've stressed the fact that Tarski's, to my mind, greatest achievement was the analysis of definitions in the reals, in the real field. He stressed, of course, the decidability, which is less significant now, or at least has to be approached in a different spirit. After he had done that, so he did the reals and the complexes. Complex is very easy. The reals is distinctly hard. It certainly was at that time. And he went on record fairly early with the following problem, which was regarded from the outset as an extremely major problem in this kind of model theory. What happens if we add exp as a primitive to the reals?
Did you say Tarski?
This is Tarski's problem. And it certainly was, for people of my generation, was regarded as one of the major problems in the subject. Now, the vigilant among you who have not seen it before may say, well, why didn't he ask about the complexes? Well, he did ask, well, rather, he didn't ask because he already knew the answer, and anyone who thinks for a second will see that the answer is bad here. Why? This is a non-Gödelian situation. Excuse me, this is a Gödelian situation. This is just as bad as full arithmetic. Why? The periods of exp to n pi I, and you can define the integers from that in various ways. Just choose your favorite way. One way would be a crude way would be to go to the rationals, take quotients of these, you'll kill your 2 pi I stuff and you'll get rational numbers, and then go back from Julia Robinson's very deep definition. That, of course, is a perverse way to do it. There are much nicer ways to do it. The best way to define the integers is to say, these are the things such that if you multiply a period by them, you've still got a period. Okay? So you can interpret arithmetic with its plus and times, so it's just as bad as arithmetic. So Tarski abandoned that, naturally enough. A curious thing I may not have time to discuss at the end is that that was perhaps slightly premature. And just in case I don't get to say anything about it, there is something at the end of the notes. There's also a meeting on this topic at Michigan in April. Perhaps somebody here can tell us the dates. On the other hand, for R, there are no periods for the exponential function. So this kind of simple argument doesn't establish anything. Now, the problem was certainly posed by Tarski in the 1930s and unquestionably was looked at by the very, very talented members of his group. And I always remember with perverse pleasure the efforts of a Fields medalist on this problem. He eventually gave up in not just disgust, rather ungracious disgust, I would say. And in fact, very little was discovered about this for a very long time. One had no real sense whether it should be positive or negative, the answer to this. I mean, I was aware of it since I was a kid, basically. I didn't ever anticipate making any contribution to it. It just seemed like a rock. There was nothing there you could get at. And then I had a little bit of, this didn't constitute a breakthrough, but it was a kind of a nice piece of serendipity. I was on leave at the Institute for Advanced Study when I was teaching at Yale, and I was already getting a bit disenchanted with conventional things in logic, and I decided I was going to do some serious study in Lie theory. So I went to the library to pick up something by Harish Chandra, and on the shelf beside it, I saw this wee book by G.H. Hardy, written in 1911 or 1912, on orders of infinity. Which I may have heard of before, but I certainly had never opened. And Hardy was engaged in a project on asymptotic analysis, attempting to make sense of Dubois-Reymond's sort of calculus ad infinity for certain real functions. It's also very conspicuous that Hardy is severely limited in his work because he didn't know any evaluation theory. Had somebody just told him the definition of evaluation, much of this would have fallen into place. At any rate, Hardy, without making it explicit, proved the following. I mean, you will not find this as a theorem in either the book or the long paper he wrote in the same time period. If f of x is an exponential polynomial, over R. Now, for me, or for a logician, an exponential polynomial involves iterated exponentials. So I could have e to the z cubed plus 7 minus blah, blah, blah. It's not just a kind of a height 1 thing, these are the ones which are intensively studied. Then f has only finitely many zeros in R. A fact which certainly in the 70s was not well known to analysts. I asked many, they didn't know it. Now, for a model theorist, this just offered a slight flicker of hope that this problem might have some tractability in it, because at least you're not going to be, to play any kind of game at all, getting an infinite discrete set as zeros of a one-variable polynomial. So that, I mean, Julia Robinson had various tricks that said if you could get infinite discrete sets in certain situations, there was a trick for getting undecidability. So this was at least comforting, that the most obvious tricks would not yield anything. So at this point, I began to think seriously about it, and I constructivized this in various ways and made some slight improvements, began thinking about constructions involving formal power series and so on. Somewhat earlier, Dan Richardson had done similar things. And then I began to work a lot with Lau van den Dries over a number of years. And we considered various things around this, but we didn't get very far. I became aware, however, that the Tarski problem was somehow connected with Schanuel's conjecture in transcendental number theory, which I'll just put up now for those who don't know it. It says that basically the exponential has no real secrets beyond its functional equation. As far as elementary algebra is concerned, it's a complex conjecture, linearly independent over Q, then the transcendence degree of Q, lambda 1, lambda n, E lambda 1, E lambda n is greater than or equal to n. So this was formulated by Steve Schanuel around 1960. He was working with Serge Lang at the time. I asked Serge, why they gave it in this form, and he's going to throw it. He says, "Oh, the numbers were just right," or something like that. Well, the numbers are fantastically right, because from this you can deduce anything you could ever imagine in transcendence theory. Transcendence of E is a triviality. Transcendence of pi doesn't take very much. Independence of E and pi doesn't take very much, and so on. So, of course, no one really I don't think, maybe there's some youngsters in the audience who will go on to prove this. I sincerely hope so. But this would be an epic result to prove this. But it has a certain flavor that the exponential is functioning somehow freely modulo its functional equation. Because clearly, if these things are linearly dependent over Q, there is an algebraic relation between their exponentials. Okay, so over time, Van den Dries and I, sometimes together, sometimes separately, started doing exponential algebra. We looked at rings with exponentials, and we proceeded formally. We constructed the free exponential ring on various sets of generators. It's not trivial to construct this. And we proved that the algebras of exponential functions on the reals and the complexes and the periodics on finitely many variables were free. Well, they were free over the constants, C or R and stuff. And I also showed that the absolutely free exponential algebra satisfied Schanuel's conjecture. Axe had done something similar, unknown to me, or vaguely known to me, but I'd forgotten the connection before. Axe approved a version of Schanuel's conjecture in a power series situation around about 1970 by using differential algebra in an extremely beautiful way. Anyway, various things came up. I mean, evidence accumulated that Schanuel's conjecture would be a help, and moreover, there was really no way to avoid it, because part of the decision procedure for R would involve you discussing the following equations. Suppose I wrote down some polynomial over Q, and I asked you whether f of e to the e to the e to the e equals 0 or not. That's part of the decision procedure. I can formulate that as a sentence. Now, nobody here knows how to do that, for sure. On the other hand, if Shanyo's conjecture is true, you do know how to do it. Because it's a freedom thing. You can easily prove from Shanyo's conjecture that this can't happen unless f is trivial. Now, this is fairly superficial and very, very far from getting at Tarski's conjecture. I also managed to show, using Shanyo's conjecture, that rather general decision problems about exponential constants were decidable. For example, if I know Shanyo's conjecture, I can decide I can decide whether a particular algebraic relation holds between e to the e, etc., etc. Okay. Now, but as I want to stress that all of this, although significant in the final solution of the decidability problem, really doesn't touch the surface, hardly touches the surface of the definability problem. Well, again, I'll cut corners with the history. It turned out that various other groups were working on this. There was very significant work done by a group at the Humboldt University in East Berlin on it, on the orders of infinity aspect of it. And the most significant work done prior to the final solution was done by a Russian real analytic geometer, Hovansky, who proved a higher dimensional finiteness theorem, which turned out to be crucial. And this is really what I want to emphasize. Suppose I consider a system of exponential equations. Let me take a special form, but it's actually completely general. Suppose I consider a system f1 x1 to xn e of x1 e of xn equals 0 down to fn the f's are polynomials, ordinary polynomials. And I impose the sort of Italian condition that the Jacobian of this is non-zero. So plus Jacobian okay, any equations and unknowns, this is really just an exponential étale situation.
These are polynomials in the usual sense, not in the composition.
Yeah, I mean, Hovansky proved a great deal more than this. I mean, one could really have I could have suppressed the exponentials here and said that these were generalized exponential polynomials. But I write it this way to bring out the connection with Shannion's conjecture. I mean, Hovansky proved a great deal more than this. He proved that this has only finitely many solutions and moreover uniformly in any sense of parameter, say the coefficients of the polynomial. This paper was published in Doklady in 1980, and a more elaborate discussion is in Hovansky's book called Few Nomials, published by the AMS. Now, this is proved using very cunning arguments. Morse theory is ultimately involved in behind things, but the essential thing is the differential equation for the exponential. And then higher, well, cunning uses of Rawls' theorem, significant uses of Sard's theorem to get into general position and so on.
How explicit are the bounds?
Sorry?
How
How?
explicit are the bounds?
This is the best question. Not very explicit at all. I mean, with enormous effort, in the case of n equals 1, the East Germans, with some assistance from me, were able to write down some kind of analog of the standard result. If you take a polynomial, you can say there's no roots beyond that point. We could do a similar thing for exponential polynomials in one variable, but it's very, very indirect. To this day, one does not know such a bound for the higher dimensional systems. So it's not very explicit at all.
These are two polynomials, not
I chose to restrict to that case now to make it look a bit like Shanyo's conjecture, but it's got the same shape as Shanyo's conjecture, because think of this as telling you something about the variety of the point x1 to xn, e of x1, e of xn. This system is basically cutting its dimension down to be n already because of the Jacobian condition. I mean, there's some hand-waving here, but that's the basic point. Now this, when we were at Wilkie and Van der Vries and I were all at Yale together in the period this became available, so this was revelation. I mean, this made us feel that it was likely that Tarski's problem would be solvable. Perhaps not the decision problem, but that one would be able to analyze definitions. Now, I am involved here in cutting a very long and complicated story rather short. I say a lot more about it in the notes. Wilkie eventually succeeded in showing, he didn't first of all show the decidability, he showed on the basis of this result and very significant general work of Van den Vries establishing this notion of O-minimal theory, which was briefly alluded to before. He succeeded in showing an elimination theorem for the real exponential. And it says the following, that every formula is equivalent to an existential formula. And let me write it in a slightly suggestive way. So every formula, let me call this formula phi of y, there exists an x1 to xn. Let me write it as h x y. The lengths are not the same necessarily of x and y here. Okay. Has, well, let me write it this way. The Hovansky system hxy. So I think of it as a system of this kind, but the y's are functioning as parameters in it. Okay? This is an individual Hovansky system over, say, Q or something, over the reals. But I think now of inserting parameters in it. You have a uniformity result in parameters. Wilkie succeeded in showing that everything is equivalent to to the solvability of a particular Hovansky system. This is an instance of what I would call a sort of étale definability phenomenon. It's really saying that the quantifiers, this quantifier range is really finite because of Hovansky. Now, this phenomenon has been coming up all the time, maybe not ever properly acknowledged. I think Anand said something about it. Practically every elimination theorem we've ever got in logic has had this feature that if there were existential quantifiers left in, they were occurring in some sort of étale configuration, or at least they had finite range. And this is another manifestation of that.
When you say Jacobian non-zero, you mean nowhere zero?
Well, no, you're looking for a solution of the system, and at that point the Jacobian should be non-zero.
Oh, just for a solution.
Yeah,
I see.
yeah. So you're looking for sort of regular
And that's-
solutions.
That's for the whole function, not for the polynomials.
That's right. It's for the whole function, but there's not much difference in this case because of special features of the exponential function. That's sort of in the calculations. That's an important point. Yeah.
Well, I'm just slightly worried because in the formulation as given, seems it can't be true unless the exponentials actually occur for one thing. Right? Isn't that right? Suppose I just have
No, but I mean, this would still be Bezout's theorem. In general, if I impose the non-singularity, if I impose the non-singularity, it would be Bezout's theorem. In fact, Hovansky uses Bezout's theorem at the base step of the induction.
and there are n equations.
Yeah, that's crucial. That it's n equations and n unknowns. This is the critical point here. Okay. Now, I just want to stress that these are. So in other words, the whole thing was our optimism. After seeing Hovansky was justified because the whole thing is controlled by Hovansky systems. It's not, of course, as tight an elimination as we've seen in the early cases because there are more quantifiers, but they've really only got finite range. Okay. Now, again, let me repeat, given that these are supposed to be historical lectures, I am suppressing a huge body of theoretical development, especially in the notion of O-minimality, to which the main contributor, after the foundational work done by Van den Ries and Anand and Charlie Steinhorn and Julia Knight, the main contributors were Wilke and Van den Ries. Van den Ries contributed the main theoretical development throughout this time. Okay, this doesn't solve Tarski's problem. For various reasons. One is, Wilke did not succeed in finding the axioms behind his elimination. See, Tarski, I've stressed the fact, Tarski's elimination for the real closed fields uses one of two sets of axioms that one might have. This result did not use any axioms at all. This is a very sophisticated thing. This was published, Wilke is usually slow to publish. This was published in the Journal of the AMS in '96. And because you didn't have the axioms, it's rather difficult then to penetrate the issue of decidability. So if you started with a general sentence, how do you get it to this form constructively, for example? And then how do you decide this? How do you decide if this has a solution? How do you decide if a Hovansky system has a solution? Well, Wilke and I, the following year, looked at this carefully, isolated axioms that were being used. They are rather complicated axioms, but they correspond typically to important analytic principles, things about solving certain kinds of differential equation, some kind of sign change property, some kind of Newton approximation scheme, etc. Logically, they're rather complicated. And we found eventually that Shannon's conjecture was absolutely involved in this. We found a set of axioms which is complete if Shannon's conjecture is true, a recursive set of axioms we found which is complete if Shannon's conjecture is true, and moreover, we were able to use Shannon's conjecture to decide these things. And that's maybe not so terribly surprising, because the point is systems of this kind are basically forcing you down to the lowest possible dimension for the transcendence degree of that point. They're forcing you down to n. Really, so it's almost as if algebraic geometric conditions are controlling what's happening to x and its exponentials. I mean, you have to work to do that. So this conjecture in transcendental number theory controls the decidability, and it controls how we will understand the structure of definable sets. And in particular, various questions in asymptotics, going back to Hardy, can in principle be decided assuming Schanuel's conjecture. This is also somewhat surprising, that transcendental number theory could possibly have an impact on how certain functions are behaving near infinity. But it does. Now, okay, according to my calculations, I have about 5 minutes left. And I think I started 5 after. I won't say any more about the development in the real analytic case. Many other beautiful things have been done in this, for example, by Lau in conjunction with Patrick Speisiger, who is in the audience. One has, to a lesser extent, been able to understand some of the behavior of the zeta function in a real situation and the gamma function, but not at this level of refinement. But one has finiteness theorems. One knows that definable sets have finitely many connected components. It's already extremely remarkable that one can obtain this. So there's a big literature on that. There's already a beautiful textbook by Van den Vries, and there will be other textbooks, no doubt, on the exponential and so on. Now, I think I'm not going to say anything about the complex exponential, but let me say something briefly about the p-adic exponential. Now, most people know that there is a p-adic exponential defined by the same series, but with delicate issues of when it doesn't converge everywhere you would like it to, and so on. And there are various other exponentials which are perhaps more natural from a model theoretic point of view. For example, for most primes, the function, say, 1 plus p to the x, is a good function on the p-adic integers. Sometimes you might have to go to 1 plus p squared to the x or something like that. But these are well-defined functions. And one can ask the question, is there something like this Wilkie work for the p-adic situation? Is there an algorithm for deciding statements about the p-adic exponential, or is there at least some control over the structure of definitions? I mean, the two don't necessarily go together. Now, again, one might have some reasons for optimism because, for example, if I consider this function for convenience because it's defined on ZP. It's a known result that things built out of this function using the rational operations have only finitely many zeros in ZP. This is an instance of Strassmann's theorem in p-adic analysis. And it's the kind of theorem which Skolem used in his work on his finiteness theorems in p-adic analysis. Strassmann. I don't know who Strassmann was or when he did it. It was a very elementary theorem about functions defined by convergent power series in these situations. Yes, I mean, one can prove also the corresponding theorems in the particular case of the exponentials are readily proved by other methods, which are more combinatorial. There are many ways to prove these things. Now, Strassmann's theorem basically says that there's something like the analog of Hardy's theorem, point of departure. So you couldn't, at least you cannot define the ordinary integers in some simple way using one variable exponential polynomials. You can also obtain effective estimates for the number of upper bounds for the number of zeros of these things. I did this a long time ago, and I discovered that van der Poorten had done similar things a little before and so on. These are quite straightforward. But again, they don't tell you much about the higher dimensional situation. Now, after the fact, we know that there is a Hovansky theorem in the p-adic situation. This emerged, well, this became known in the course of work, again, by Denef and van den Ries. Denef and van den Ries in 1986 managed to do something I'd been trying to do for a few years beforehand. I published some fragmentary stuff on it. They managed to extend my quantifier elimination from the p-adics, or from the p-adic integers, to the p-adic integers equipped with basically all convergent power series. But they needed them all to get a decent result. The van den Ries then did look at issues around, and they gave a uniform treatment of such an elimination theorem for the reals and the p-adics. This was a fantastically beautiful paper in the Annals of Math around about 1988. So they gave a new treatment of the theory of real subanalytic sets, and they invented a theory of p-adic subanalytic sets just by motivations of definability in the p-adic analytic situation. And their analysis revealed various finiteness phenomena in more variables. Crudely analogous to what one was observing in the reals, but of course different because the topologies are so very different. Anyway, using that work of van den Ries and Denef and some other things of van den Ries, for which I do, I think, give him credit in the notes, I was able to show, I never published it, but there is a handwritten manuscript if anyone is interested in seeing it, provided I can find it. I think it's in a drawer in Edinburgh somewhere. But I did it in Berkeley in 1990. I was able to show a very rough analog of Wilke's result, actually before Wilke did his, for the p-adic exponential. I was able to show that, well, okay, the situation is quite interesting. You start with the p-adic exponential. It doesn't really matter where you take the x, where you take this function here. This is not significant. Now, you would like to get an elimination theorem that says that everything's equivalent to an existential formula. Not necessarily with all the Hovansky stuff in it, but an existential formula at least. Okay?